So just a reminder that you guys still have chance to sign up for science fair judging. You'll get 3 bonus points for doing that. Bonus points are important particularly for those people who end up with grades like or scores like 78.5 or 88.5. So last semester a couple of people ended with this kind of score and they got C. Okay, and I gave lots of opportunities to get bonus credits, but they never took that opportunity, so they ended with that. And some students took the opportunity to get the extra credit, and they got, because of the bonus points, bonus extra points, they ended with like B grade for that. Okay, so for this one, like some students ended with like B grade and some ended with A with extra credit. So particularly in these kinds of situations, extra credit points would be very helpful. It's not required, but still it's always nice to get some extra credits in case if you end up with like this kind of situation. Okay, so it's 11. Let's get started. So today we'll work on worksheet 11. So those who are on Zoom, you can download worksheet 11 from Blackboard. We'll talk about spring force today. So we have talked about different kinds of forces so far. We talked about tension. We talked about drag force. We talked about gravitational force. Okay, all these kinds of forces. Today we'll talk about spring force. So imagine that you are stretching a spring. Okay, so we have a spring, and this is in a normal condition when it's not stretched. When a spring is not stretched, we call this condition equilibrium condition. Okay, so this is in equilibrium state, or you can say normal state. Now imagine that you stretch the spring by some force. Okay, so you're applying some force, and when you stretch the spring, what happens is you feel some force that pulls you inward. Okay, so you feel some force in the direction opposite to the direction you apply the force. If you're applying the force this way, then your hand, let's say you're also applying in this direction, then your hand will feel the force in this direction and in this direction. And these forces are exerted by spring, okay, this spring, to restore its original state or to restore its equilibrium state. That's why this force, which we call spring force, is also called restoring force. Okay, so spring exerts restoring force in the direction opposite to the direction of applied force. So instead of elongating the spring, let's say you compress the spring. Okay, so you push the spring inward by applying some force. So this is extension, and this is compression. So when you compress the spring, you will feel the force in the outward direction exerted by the force. Okay, so you will feel this spring force, and it will be opposite to the way you apply the force. So when you apply these forces, whether to extend the spring or compress the spring will be the length of the spring would be changed. Okay. In this case, the length is increased. In this case, the length is decreased. So the change in the length of the spring is directly proportional to this force, okay, spring force or restoring force. So this is directly proportional to the restoring force. So delta L, sometimes it's denoted by delta L or sometimes delta X, both are fine. So delta L is equal to F spring, or I mean not equal, proportional to F spring, or sometimes you will also see delta X is proportional to F spring. Okay, so greater this force. Let's see, I have a comment from someone. Can you go back up? Okay, so someone wants to see that. Okay. Yeah, if I'm going too fast, let me know. I can slow down. Yeah. So this means greater the restoring force, greater is the change in the length. Okay. Now when we have this kind of proportional sign, we can turn that into equal sign by using some kind of constant. So we can also write this as F spring is proportional to delta X, okay, delta L. Just they depend on each other. Okay. The delta L depends on F spring and F spring depends on delta L. So the meaning of this one is, the physical meaning is greater the change in length, more the force you feel. Okay, that's what you experience in your real life. So if you stress longer, you feel more force. If you just stress a little bit, you feel a little bit of force. So more the change in length, more is the force. More the force you feel, or more the force, or more the restoring force. Okay. So you can turn this into equal sign. F spring restoring force is equal to, and by the way, we also need a negative sign here. Okay. So this negative sign implies that restoring force, negative sign implies restoring force is opposite to the displacement, or opposite to the change in length, direction in which the length is changed. Meaning, if you increase the length, by stretching it. Okay, so you are increasing the length in this direction. Then the restoring force would be opposite to that. So this would be, so this is delta x, displacement is this direction. Then restoring force would be opposite to that. Okay, to signify this difference in the direction, we put minus sign here. Okay, likewise, if you compress the spring, okay, you compress the spring, so delta x would be this direction. The change in length would be this direction. Then the force would be opposite to that. So this would be the direction of the spring force or restoring force. Okay, so they are always opposite to each other. So we can write minus delta L. So to write equal sign, we need some constant. In this case, we denote the constant by letter K, okay, times delta L. So this formula is called Hooke's law. H-O-O-K-E-S, Hooke's law. And this constant K, which is proportionality constant, is called spring constant. And different springs have different value of this spring constant. So we'll see in lab today and tomorrow that different springs, you'll get 5 or 6 springs, and you will find this value for each of those springs. Basically, this tells us, this K spring constant tells us how stiff a spring is. Stiffer the spring, greater would be the value of K. Okay. So let's look at number 1 from worksheet 11. You have 2 springs, one with spring constant K1 given by 15.5 newtons meter squared. That's just meter, okay, not meter squared. Sorry, there's a typo for on the unit. So K is measured in Newton per meter. So the unit of K is Newton per meter. And then we also have another spring which has K of 28.5 Newton per meter. So which spring do you think is stiffer? As I told you, greater the value of K, stiffer the spring is. So you can decide which one is stiffer. If you stretch the spring by 2 centimeters, how much restoring force will each of the spring exert on you? Okay, so we can just use the formula. And when we find this kind of numerical values, basically we don't need to worry about this negative sign, because negative sign implies only the fact that restoring force and displacement are opposite to each other. So we don't need to just worry about that negative sign. We can just use K delta L, okay, for the formula. So on B, it's asking to find the restoring force. Okay, so, or restoring force means spring force. So we want to find spring force. K for the first spring is 15.5 Newton per meter, and the springs are stretched by 2 centimeters. So this is in Newton per meter, this is in centimeters. So we need to make the units uniform. So change centimeters to meters. So how do you change centimeters to meters? So 1 centimeter is how many meters? 0.01 meter, right? Or 1 meter is 100 centimeter. 1 centimeter is 0.01 meter. So we can cancel centimeter and centimeter. and then this meter cancels with that meter. So 15.5 Newton times 2 times 0.01. So that would be our spring force or restoring force, which is 0.31 Newton. Okay, I got that. And you can do the same thing for the second spring also. Exactly same calculation, but for second spring you will have different spring constant. Okay, so you'll have this to be 28.5. Stretching is same, so 2 centimeters, conversion from centimeters to meter, and that will give you some value. Okay, you need to calculate that. So that's one. Let's look at number 2. Assume that a bungee jump cord with the spring constant K given by 525.5 Newton per meter obeys the Hooke's law. So whenever it says it obeys Hooke's law, let's see, someone is asking question here. What did we do for part A of 1? Part A of 1. So which spring do you think is stiffer? Which 2? Yeah, so the second spring is stiffer because it has greater spring constant. Okay, greater the value of K, stiffer the spring is. Okay, so number 2, whenever the question says it obeys Hooke's law, that means you can apply this formula. Okay, obeys Hooke's law means spring force is equal to K times delta L. Again, sometimes you will also see delta X here, they are same. So K is given 525.5 Newton. So we need to find delta L or delta X. Okay, and when a person with mass 65.5 kilogram dangles on the cord. So when the person dangles, how much force does the person exert on the string or the cord? Okay, so you have a cord. So this person is dangling. So how much force does this person exerts? mg, yeah. So the weight of the person. So mg would be the force exerted by the person, and the cord will also exert the same force. Okay, from Newton's second law, Newton's third law, for every action there is equal and opposite reaction. If this is the force exerted by the person on the cord, then the cord, which obeys Hooke's law, will also exert this spring force equal to that force. So in this case, spring force would be equal to the weight of the person, which is m times g. Okay. So mass is 65 kilogram, 65.5, g is 9.8 meters per second squared. So what you get, 6 641.9 Newton. Now, once you have that, you can find delta L. So, let us do that. Why don't you guys find delta L by using this formula? So, we want to find delta L. Rearranging this formula, we can get delta L is equal to F spring over K. So, what is the number? 641.9 over 525.5, that is Newton per meter. What did you get? 1.2 meters. Okay. So, the person will stretch the cord by 1 to 1.2 meters, okay, about that much. So, that is number 2. So, that is about the springs or elastic material, but sometimes we also compress or stretch rigid objects, okay, something like wires or rods. So, those things are also kind of springs, because if you look at the microscopic, if you look at those objects microscopically at microscopic level, they have these molecules. Okay, if you consider an iron rod or some kind of steel rod, at microscopic level they have these tiny molecules and they are connected by bonds. Okay, you might have seen this in chemistry. So, they have these bonds, and bonds usually act as tiny springs. Okay. So, we can model these bonds by tiny springs. So, that means at microscopic level, even a very stiff object or rigid object could act as a spring. Okay. So, this would be your iron rod, and you can actually pull the iron applying the force, and then you can stretch that. So, that means the stretching how do you spell that? Stretching and compressing is possible not only for springs, but also for rigid objects like metal rods or wires. Okay. Even rocks, okay, metal rods, wires, or even rocks. You can stretch or compress rocks also, although you need lots of force to do that, but you can still do that. Okay. So, the stretching of these rigid objects, the stretching or compressing the rigid objects require higher forces. For springs, you don't need as much force, but for the rocks or metals, you need lots of force. Okay, and the change in the length, which is stretching or compressing, the change in length of those objects, means the rigid objects, is objects depend on three things. What are those three things? Can you guys guess? When you try to stretch a wire, what are the factors that affect how much stretch you can put on the wire? Just think about it physically. Yeah, it depends on spring constant, but let's forget about that for a second. Okay, so we'll come back to that later. What else affects the stretching of the wire? Sorry? Yeah, exactly. So the amount of force you put, the bigger force you put, the more stretching you get, right? It depends on force. So delta X or delta L depends on force. Greater the force, more is the stretching. What else? Let's say, sorry? Exactly, yes. Yeah. So you have a thin wire and a thick wire, right? So the thickness is defined by the cross section area. So this is cross section area of that. That's the cross section area of that. So thinner the wire, easier it is to pull. Okay, more easily it stretches. That means this delta L is inversely proportional to the cross section area. Thicker the wire, less is the stretching. Thinner the wire, more is the stretching. What else? You have a short wire and a very long wire. Which one would be easier to stretch? You have a short piece of wire and a long piece of wire. Which one would be easier to stretch? Longer wire. So it depends on the length, how long it is. Okay, so we can combine these three things into a single relationship. So the stretching or compressing of a wire, or not just wire, it could be any kind of rigid object. It could be a metal rod or a rock, depends on force, length, and area. Okay, so that's that. And again, we can turn this proportional sign into equal sign by inserting some kind of constant here, and in this case we'll be using constant called y. Okay, this y, and this constant, which we call proportionality constant, proportionality constant, is called Young's modulus. It is named after a scientist named Young's modulus. And it depends on materials. Okay, or you can say it is a property of a material. What that means is different materials have different values of y. For example, copper may have different one kind of value, whereas iron can have different kind of value, gold can have another kind of value. So different materials have different values. Okay. So usually in engineering they don't use the term force or length. Instead they use different kind of terms. So we can rearrange this equation and write it as, so divide both sides by L, we get this and this cancel. So delta L over L is equal to y f over a. So this is fractional change in length. Okay, change in length over total length is what fraction of length you changed when you apply the force. Fractional change in length, and this is force applied over some area, over a cross section area. So they call this as stress. Okay, stress is how much force you apply over some area, force over area, and they call this strain. Okay, particularly in engineering. So strain is equal to Young's modulus times stress, or you can write Young's modulus is strain over stress. Let's see. No, I think I take it back. So I take it back. So here this y would be on this side. Okay, you can, if you want, here you can write 1 over y, but Young's modulus we put on this side. It's a constant. You can put the constant anywhere. Okay, either you put here this side or this side, doesn't matter. If somehow you want to put here, then it would be 1 over y. Okay? But here we'll put on this side y, Young's modulus. Okay? So that's the proportionality constant. So our y, Young's modulus, is on this side. So basically we got f over a is proportional to delta L over L, and then we changed this into equal sign by plugging this y, delta L over L. Okay, that's what the actual thing is. And this thing is stress, this thing is strain. Okay, and then we have y. So y is stress over strain. Okay. So Young's modulus could be defined as the ratio of stress over strain. In other words, the physical meaning of this one is Young's modulus tells us what fractional change in length you can produce by applying some force over an area. Okay, that's the physical meaning of Young's modulus. So greater the Young's modulus, more change you can produce. Or in other words, you can also say this one, okay, more accurately. Alternatively, you can also say how much force you need to apply over an area to produce to produce some fractional increase in, so fractional change in the length. Okay, so the relationship here is more the fractional change you need so more the fractional change you want to produce in a wire or some kind of rod, more the force you need. Okay. So consider, let me give you an example that will make it more clear. You have a gold wire and iron wire. Which one will require more force to produce the fractional change? If you have a gold and iron, you might have talked about the property of gold in chemistry. Gold is malleable, and what is the term you use? That could be easily stretched. I don't remember the term. Yeah, some kind of elastic. Yeah, elastic, more elastic. Gold is. So that means you need more force to produce a certain fractional change compared to gold. More force to produce fractional change. In case of iron, you need more force to produce fractional change compared to that of the gold. Okay. So that means this will have higher Young's modulus. So let's look at some of the values of Young's modulus. Let's see some values. So these are some of the values of Young's modulus for different kind of material. Oops. What is it? So cast iron is 20 times 10 to 10 Newton per meter squared. To produce a fractional change in cast iron, you need that much force, which is a very, very large amount of force. Okay, you also have this 10 to 10. Okay, aluminum needs only 7 times 10 to 10. Okay, glass needs even about same as aluminum. Concrete needs 3, wood needs 1. So cast iron is very, very strong. Okay, even by applying such large force, it produces very small fractional change in the length. That's why we use cast iron or steel to build structures, because they do not produce much stretching. Okay. So let's see. So let's look at number 3 to use the formula that we just derived. So a small elevator with mass of 550 kilogram hangs from a steel cable that is 3 meters long when not loaded. The wires making up the cable have a total cross-sectional area of 0.20 centimeters squared, and with a 550 kilogram load, the cable stretches 0.40 centimeters beyond its unloaded length. Determine the cable's stress and strain. So we want to find stress. Stress is force over area. So what is the force of this elevator on the cable? How much force does this exert on the cable? It's mass of the elevator times g, right? So force is mass times g, and area is area of this cable, okay, cross section area of the cable. So the cross section area of the cable, if you magnify the cable, you will see something like this. Cross section area is this cross section area, which is 0.20 centimeters squared. So mass of the elevator is 550 kilogram. G is 9.8 meters per second squared over, we have meter here, but we have centimeter here. So we need to convert this centimeter to meter. So 1 centimeter is 0.01 meter, but we have centimeters squared, not just 1 but 2 centimeters, centimeters times centimeters. Okay, that's centimeters squared. So then this would be 0.01 meter times 0.01 meter, which would be 0.0001 meters squared. So that is 0.20 times, this is, the conversion is 10 to negative 4th meter squared. Okay. So this is basically 1 times 10 to negative 4 meters squared. Okay. So that's what we need to use to convert from centimeters squared to meters squared. So do the calculation, you get the number. And then we need to find strain. Strain is fractional change in the length. Fractional change is delta L over L. Delta L, it says the cable stretches by 0.4 centimeters beyond its original length. Its original length is 3 meters. Again, one is in centimeters and the other one is in meters, so we need to make them uniform. So either change centimeters to meters or meters to centimeters. Okay. So I will change meter to centimeter, that would be easier for me. So multiply this by 100, that changes meters to centimeters. So do the calculation and see what you get. So what you got for the first one, stress? It should be a big number, yeah, because you need lots of force to produce that small stretch. Because when you stretch a wire, it takes lots of force. So what you got? 2,690,000. Tell me the number in scientific unit. 2 point. So when you round it 2.6, should it be 2.67? 2.7. Okay, so by rounding off 2.7 times 10 to 8, right? 10 to 7. Newton per meter squared. Okay, a large force. Okay, so strain. What did you get for the strain? Yes. So strain is a ratio of two lengths, so there is no unit. Okay. So this is the fractional change in the length, a small fractional change in length. So in order to change, or in order to have a small fractional change in length, you need large force, which is what we usually see when we stretch wires or metal rods. Now we want to find Young's modulus. So Young's modulus is Y. Y is stress over strain. Stress is 2.7 times 10 to 7, and strain is 1.33 times 10 to negative 3. Let's see what you get. So this is Newton meter squared. There is no unit down here, so this means Y would also have the same unit as stress. Okay. So number 4 is similar to this one. Let's real quickly do number 4 because we still have a couple of minutes left here. So let's look at number 4. So on number 4, we are given Young's modulus. Y of the material is 2.8 times 10 to 11. So there is a typo there. It's actually 11, not 1 on the bottom. So Newton per meter squared. The cross section area of the wire or the material is 0.50 times 10 to negative 2 meters squared. Its original length is 1 meter. So the first one is asking, what is the stress exerted on the cable? So stress is force over area. So you are exerting force of 10 times 10 to 3 Newton, and the area of the cable 0.5. It's in centimeter. No, it's in meters. So 10 to negative 2 meters squared. Okay, so that's the stress, and then we also want to find strain. So strain is delta L over L, but we don't have delta L. So what should we do? Okay, we don't know this, but we know the formula for stress and strain in terms of Young's modulus. So Young's modulus is stress over strain. So strain, you can rearrange that. So strain would be stress over Young's modulus. So you can find that. And then by how much the cable is stretched. So for part B, we want to find delta L. Now we can use strain is delta L over L, and delta L would be strain times L. So what did you get for stress? If you want to share your answer here. Newton meter squared. What you got for strain? Okay. Should it be negative? I think it's no. 10 to 16 or negative 6? I don't think that's the right one, because 6 over 10 to 11 it should be. Can you redo that? So put this whole thing in parentheses when you do the division. Okay, so what's the number? Okay, that seems reasonable. And then that times the original length gives you the delta L. Okay, 7.14 times 10 to negative 6 meters, or not meters, sorry, just no unit. That's the fractional change. Okay, so that's all for this lecture. We'll continue this in the next lecture.